going in this direction, and air is going down in this direction. So again, it's a counter current arrangement. And for the counter current arrangement, this is what we have. Is it clear now?
Yeah, Doctor, thank you so much.
Okay, now let's look at some other effort that we have done. That work that we had a project that we were working in here in the university. That was something in 2013 or so. And we wanted to come up with some sort of what would be a good design for an HDH system. And we came up with this piece of work that we did, it was published in 2014. And that was basically, we needed to give a guideline for quick estimation of how would be the size, how can we design an HDH system without having to do much calculations, without having to go through the analysis. That was something like an engineering practice. If somebody needs to give a proper size of an HDH system without having to go through rigorous calculations. So we have created some charts, and these charts are being utilized to do that. I'm putting we'll put that in a paper, and this is the details of the paper, the title, the authors, and this is the title of the paper. It appeared in a journal called Desalination Journal. That's the volume. It was 2014 from pages 10 to 21. And we were looking into two systems. One of them is what you see here is a water heated system. You have a pump which is bringing seawater in. The seawater is going to be preheated in the dehumidifier through the transfer of heat from hot and humid air. Water is going to be preheated from 1W to 2W, and then it will be further heated to 3W. This is the highest temperature of the whole cycle, highest temperature of the water. It will be sprayed. It will transfer heat to the air which is coming in a counter current arrangement and leave at 4W. Whereas the air is going through a closed cycle. It leaves the dehumidifier. The fan is pushing it into the humidifier where it will be heated and humidified, and the hot and humid air is going to condense. Water vapor will be condensed out, and the air is going to go through the cycle again. So this is a typically open water, closed air, water heated HDH system. The problem statement is saying that we need to basically size an HDH system that should provide us with a production rate of 10 liters per hour. Actually, to be honest, we have taken this example, we have done it, and after that, based on the results that we got from that example, we built the unit, the one that I showed you in the class of, was it last Monday, the one which is very well insulated, and we have it in our lab in building 26. And the unit, after building it, we found that for water heating, yes, we can get 10 liters per hour, but definitely at a certain mass per rate ratio. The feed seawater supply is coming at 30 degrees centigrade. We had water coming because normally, if you measure the temperature of the Gulf water in summer, you will find it almost at 30 degrees centigrade. It has a salinity of 35 grams per kilogram, or in other units, you can do it per unit volume as 35,000 ppm, which is typically what you see in the Mediterranean or the Atlantic Ocean. A little bit higher than that. Maximum water temperature, so the heater is going to heat the water to 60 degrees centigrade. And we assume the effectiveness of both the humidifier and the dehumidifier to be 85%. So these are the kind of information that we have, and these are the information that we need to build the system. We have already done a lot of analytical work. Actually, it has been done using the engineering equation solver, and we created some figures, graphs. We are going to make use of these graphs to estimate the right size and the performance parameters of this system. What we need to do is to calculate the rate of thermal heat input to whatever a solar collector or electric heater, whatever, but what's the QN that we need here? How much seawater should flow in? Remember, the only number that we have specified is this. We're talking about 10 liters per hour of fresh water or pure water production. So how much seawater would be here? Why are we asking this question? Definitely we need it for something. We needed to see what kind of pump we need to buy from the market so that it can supply this amount of water. And how much air, because knowing the flow rate of the air will enable us to go and buy the right blower that should blow air within the system. And then what should be the size of the humidifier? How high is it? Height, width, and how much should be the surface area for the dehumidifier? If I'm going to go and buy heat exchanger elements, so how many elements so that they give me the required surface area for the dehumidifier? So the answer of these for us now will be done through going through these figures. So we have those figures here, and we're going to utilize these figures to determine the quantities that we wanted. So there are things that we know already. We know that the minimum temperature is 30, as you can see it here in the figure. I'm looking at the figure here at the right, upper right, and the maximum temperature is 60. So this figure is right for these minimum and maximum temperatures. If the minimum and maximum temperatures are not 60 and 30, then you have to look for another figure. And we have actually, maybe 1 year later, we have come up with, I've been working with a couple of students who are attending a course of desalination. I think it was advanced desalination. And we came up with a paper that is doing the same analysis for different temperatures. And by the way, the two students have become both doctors now. One of them is Dr. Naif Qasim. He's an assistant professor in the aerospace department. And the other one is Dr. Binash Imtiaz, and he is doing his postdoc in the research institute. And now, based on this information that we have, the kind of inputs that we need to take to these figures are basically the effectiveness of the humidifier and the effectiveness of the dehumidifier. This is what we need for these figures. And these two values have been already assumed in the problem statement. If you remember, we said that we are going to work it out with an effectiveness value of 0.85. So what we are going to do, look at this figure. The figure at the top here, it is providing us with a goal. So you can get the goal from here. Knowing what? Knowing the effectiveness of the dehumidifier and the effectiveness of the humidifier, which is one of these. Which means that I need to get here to the value of 0.85, construct a vertical line, sorry, it should be vertical, and then it's going to intersect with this 0.85, as you can see it here, and then we make a horizontal line, and then we can calculate what's the value of the goal. So now you got the goal without having to do any calculations. And then we need the optimum mass flow rate ratio. So again, the effectiveness of the dehumidifier, 0.85, effectiveness of the humidifier is here, and then you can get the optimum mass flow rate ratio. Then we have effectiveness of the dehumidifier is 0.85. For the humidifier, it's 0.85 also. So from here, you can get what we call the recovery ratio. So here, all what we know is the effectiveness of the humidifier, the dehumidifier, and based on that, we could obtain three important parameters. One of them is the goal of the system. Second is the optimum mass flow rate ratio. To remind you, optimum mass flow rate ratio is basically m dot of the seawater divided by m dot of the air. And then we have the recovery ratio, and the recovery ratio by definition is given by this. And by the way, the recovery ratio, it's a percentage. So this means that the value is 0.0306. So from these three figures, we got these three values: GOR, MR, which is the mass flow rate ratio, and the recovery ratio. Then from these three values, we're going to get the rest of the parameters that we want. The latent heat of evaporation or condensation is HFG or IFG is given as 2,345 kilojoule per kilogram. There's no Kelvin here, I'm sorry.
Doctor,
Yes.
I have just a question.
Go ahead.
In this example, the dehumidifier effectiveness value was given in order to find the other three values.
Yes.
Is it always going to be given, or would they give us another value, for example?
Look, when you are talking about problems like this, then as you have been dealing with problems in general, if it's a problem that you have to solve by hand, then either I should provide you with the effectiveness, or I should provide you with the inlet and outlet conditions for the humidifier and dehumidifier so that you can calculate the effectiveness.
The inlet and outlet, whether it was air or water.
Exactly, yes.
Okay, perfect.
So that you can use this information to obtain the effectiveness. Otherwise, you cannot proceed in the problem. In real life, what we do is that we go in iteration, because you need to build a unit.
Yes.
In order to build a unit, then basically what you need is to come up with an estimate. Don't know the size, don't really know the conditions. So you just go through an estimate, and then you iterate it until you reach for what's going to be the size of the system. Or you make assumptions like that. You say, I'm going to plan to make an effectiveness of maybe 70 or 75%, and then you build the system and you keep on trying. This is, I mean, if you want to go ahead and build it on the ground. You say, for example, typically for humidifiers, you expect an effectiveness of 80%. So you base your calculations on 80% effectiveness. And then you would know that by experience, when you are building a humidifier using packed bed, which is structure packing, then typically that's the value that you get. But problems that you are going to solve by hand are going to be more definite.
Yes.
The values should be given to you. Okay?
Yes. Thank you.
Yeah. You're welcome. Next. Now, remember, we know the GOR. We know the mass flow rate ratio, m dot water over m dot air, m dot seawater, of course. And then we have the recovery ratio, which is the flow rate of the fresh water divided by the seawater flow rate. And this is where we are going to start. Because if you remember, this example was set to obtain 10 kilograms per hour, or 10 liters per hour, since both are the same. So basically what you need, you have this freshwater production. You need only to change it or to convert the unit so that it becomes kilograms per second. Knowing the freshwater flow rate, knowing the ratio is 0.03, then you can calculate the seawater flow rate. So from this recovery ratio definition, we're going to calculate how much seawater should be brought to pass by the dehumidifier. Knowing the mass flow rate of the seawater and knowing the optimum mass flow rate ratio, so this is m dot of the seawater that we have calculated in the previous step, and this is the optimum mass flow rate ratio from which we can calculate the mass flow rate of the air. So from here we calculate the mass flow rate of the air. Now, having known mass flow rate of the water and mass flow rate of the air, this is a good step toward the analysis, that if we need to do analysis for the system. And one more thing, we know the GOR is 0.93 from this figure, which is basically this value, What's the definition of the GOR? It is m dot fresh water, which is definitely we are going to change the 10 kilogram per hour into how much kilogram per second. This is going to be multiplied by IFG, which has been given as 2345 divided by Qn. What are we going to do with this equation? We know the GOR. We know the flow rate of the fresh water. We know HFG or IFG. So the only unknown becomes Qn. So you determine how much heat you need to add to the system. If you are going to use an electric heater, you go to the market and buy a heater with whatever, 3 kilowatts, 4 kilowatts. It depends on the value that would come from here. So we used the three figures here to determine three quantities: GOR, mass flow rate ratio, and recovery ratio. From the recovery ratio, we could obtain the flow rate of the seawater. From the optimum mass flow rate ratio, we can obtain the mass flow rate of the air. And from the GOR, we obtain the value of Qn, which is needed to run the system, which is what you see here.
Doctor?
Yes, go ahead.
Regarding the mass ratio, the flow rate water is going to be the summation for both, right? Fresh and seawater. Same for air. It's going to be dry and humid. Yeah.
For the air, we are only considering dry air. That's it. So m dot air is m dot dry air. If you remember from the analysis that we did, we said the air flow rate does not change as it's moving in because we are considering dry air. Then this air is going to carry some water vapor from the humidifier and dump them in the dehumidifier. This water vapor is basically the m dot air multiplied by the difference in omega of the air outlet minus omega of the air inlet. But when we are writing the expression m dot air, what we mean here basically is just dry air. Okay? For your question regarding the water, the m dot water that we calculated is the m dot water that's going to enter the dehumidifier. It will be heated as a whole in the heater. And then when it goes to the dehumidifier, it is going to be divided between m dot brine plus m dot evaporated to the air. The quantity evaporated to the air is basically, again, m dot air into omega 2 minus omega 1. So this is how we're going to deal with masses in the system. The m dot dry air is not changing. It is the same. It is going in a closed loop and it is dry air. And then the seawater is going to enter to the dehumidifier as this value. It will enter the heater as the same value. And then when it goes to the humidifier, it will be sprayed. Part of it will be carried by the air. This is the m dot evaporation. And part of it will not evaporate and it will flow as brine out of the unit. Did I answer your question?
Yes, thank you so much.
Yeah. Now the GOR, this is what I showed you in the previous slide. GOR is m dot fresh water, HFG over Qn. From here we can calculate the Qn. So I can go to the market and buy like a 3.5 kilowatt heater, and then I can put it in a box where water is going to pass, and this is how I can heat the water. Or you can look at solar water heaters that can provide you an average with 3.5 kilowatts. Or you can go for, if you are looking for desalination and air conditioning, you can go for a system that's going to reject heat to the surroundings at this value, whatever. From the recovery ratio, we could obtain the flow rate of the seawater supply, which is this. And then from the optimum mass flow rate ratio that we got from the figure, you can get flow rate of the air. Now, we are going to make use of this information for sizing the unit. The humidifier is assumed to be either a cylindrical compartment. We used to do that previously, like get like an 8-inch pipe and cover it from the top and the bottom, and then put sort of a tube in, and then a shower head so that it sprays the water. Or it can be a unit of square or rectangular cross section. And this is what we are doing now because we are interested to see what's going inside. So that's why we need to be like transparent. So we buy acrylic sheets and we cut them and weld them so that they have this shape. As you will see in the video, which is there in the blackboard, you see that we have built ourselves a humidifier and dehumidifier, and they are all made of acrylic or plexiglass, so they are transparent. Anyway, we are using an expression here that we borrowed from the analysis of cooling towers, which is talking about what we call the water mass flux. So in cooling towers, the water mass flux values would vary between 1.5 to 4. So we selected 1.5. We said that the mass flux which is nothing but m dot divided by the cross-sectional area, which units are kilogram per second meter square. Typical values for the mass flux are somewhere between 1.5 to 4. So we selected a value of 1.5 as our mass flux, and we assume that this is the one. And we know the mass rate of the seawater. We have already obtained it in the previous step. And we have also known the value of the mass flux. We have assumed this value. So with this and that, you can come up with what should be the cross-sectional area of the humidifier. And when we did that, we came up with a cross-sectional area of 0.06 meters square. Now it's all up to you to assume that this 0.6 meters square is going to be in a circular shape or in a square shape, whatever. We assume the square shape, and accordingly, the width of the unit here came to be 0.25. So you need your humidifier to be 25 centimeters by 25 centimeters in width. Then, next step, what about the height? Now, for this humidifier, we are going to put packing material. Packing material normally is going to have a certain pattern, which we prefer structured packing. We use the cellulose. Normally, practically, when we build a system here, like the ones that we built in the lab, we use the cellulose packing, which is used for desert coolers, المكيفات الصحراوية. And going for the packing material, we use this figure that we have generated, knowing the optimum mass flow rate ratio. For our case, it was somewhere here, 2 or 2.1, something like that. We construct a vertical line, then it will hit. Now we have solid lines that are for inlet water temperature to the humidifier, which is maximum temperature as 50 or 70. Ours is 60, so which means that we have to visually interpolate between the two lines. The value of the effectiveness of the humidifier is 0.85, which is the triangle. So it is this figure and this figure that we are interested in. The lower one is at 70 degrees centigrade. The upper one is at 50. So our value should be somewhere here. So this is going to be the point that we want. We are going to construct a horizontal line to tell us how much should be the height of the packing material. And when we did that, we found that the height of the packing material is almost 1 meter. So we have to bring packing material of a height of 1 meter and put it in the unit. And this is how we determine the height of the humidifier. Basically, the humidifier is not going to be exactly 1 meter, but you need some space on the top of this is the height of the packing material. you need some space on the top to put a shower head and some space at the bottom so that you can collect the brine before you take it out. So if this is the case, for example, and the height of the packing material is 1 meter, then we can use a height of the humidifier of 1.5 meter, for example. So 25 centimeters on the top to put a shower head or any like sprayers for distributing the water. And at the bottom, just it will be sort of a small tank that collects the brine and before you take the brine out. Now, the next step, now we have sized the humidifier. The dimensions are going to be 25 centimeter by 25 centimeter, and the height should be somewhere higher than 1 meter. So that is going to help us to size the unit. Next is to size the dehumidifier, and to do that, we are going to calculate the heat capacity rate of the two fluids in the humidifier. In the dehumidifier, we have air coming in and we have water coming in. The heat capacity rate is nothing but m dot into Cp. So we calculate mass flow rate of the seawater into Cp of the water and mass flow rate of the air into Cp of the air. And then we compare these two values. So this is the heat capacity ratio for the air. This is the heat capacity ratio for the water. So the lower one of them is the air. So this is basically, if you remember from heat exchanger analysis, this is going to be our Cmin. This C is nothing but m dot Cp. So we calculated it for the air, we calculated it for the water. So this heat capacity ratio is equal to, the heat capacity ratio basically is Cmin, which in our case is for the air, over C maximum, which is for the water, and this gives us this value. Now from figure 11, for this heat capacity ratio of 0.146, you make a vertical line, and this vertical line is going to hit the line of the effectiveness of the humidifier, of the dehumidifier, I'm sorry, and then you can determine based on that what is going to be the number of transfer units for the unit. The definition of number of transfer units, if you remember, this is m dot Cp over, sorry. The number of transfer units is basically, isn't it U into the area over Cmin? We know this value now. We know Cmin, we have calculated it. We are going to estimate an overall heat transfer coefficient of about 10 watt per meter square Kelvin. And then you can calculate from here what should be the surface area of, which is the heat transfer surface area. If this surface area is going to be done in a form of a long tubes, then this is going to be, for example, pi dl. If you are going to do it with the number of tubes, then it will be n into pi dl. Suppose that you selected the length of your heat exchanger does not exceed 1 meter, and you have tubes of a certain diameter, which you can find it in the market, then you can determine how many tubes that you need, and then you can build a heat exchanger here. Or alternatively, once you know estimated an overall heat transfer coefficient, this is another figure. So this is, we can say here and say, or if you know the value of the overall heat transfer coefficient, that can be estimated here. There are correlations to do that, and based on the effectiveness of the dehumidifier, and we are considering a water heated cycle. So from here you can determine what's going to be the size of your dehumidifier in terms of meter square. In our case, we needed a heat exchanger to be built that has 11.7 meters square. Definitely in the market you will not find 11.7. So you can go for 12, for example, or 13. It depends on what's available. And actually the way that we are doing for this is that we go to the market and we ask for the heat exchangers which are used for cross flow analysis for the air conditioning units. To remind you, it's something that looks like this. And normally are finned. Some of them are slightly different, but more or less they share the same kind of arrangement. Some of them may have like a header and another header, one for the inlet, one for the outlet. Tubes are extended between these two headers, like the radiator of the car, and these tubes basically have fins. So it's typically sort of a cross-flow heat exchanger that can be used so that water is going to pass inside the tubes and air is going to pass across it. What we do normally is that we go to the market and we count the number of tubes, we see what is the diameter of each one of these tubes, then you can calculate the total surface area. So you can get a point in the market of 3 meters square. If the total area is 11, then we need 4 units of this, and the 4 units are going to be placed as our heat exchanger or as our dehumidifier. The same thing that we have shared so far in that example can be repeated in another HDH system that could be an air heated cycle. The one that we have done so far was a water heated cycle. What you see in front of you actually is a modified air heated cycle. What is the difference between the air heated cycle and the modified air heated cycle is the location of the air heater. For a typical air heated cycle, the heater is at the inlet of the humidifier. For a modified air heated cycle, the heater is at the exit of the humidifier, which is this. This system has been shown to be thermodynamically better than the air heated cycle, and that's why we are considering this. So you can build your system to satisfy the 10 kilogram per hour. Use the previous steps that we have done so far until we reach it for this slide, which is number 13. So slides from 1 to 12 is considering water heated cycle. From 13 onward is going to look at the air heated cycle. What is unique about the air heated cycle, the modified air heated cycle? Is the location of the heater. And the location of the heater here is at the exit of the humidifier. You are heating the air here, and then it will enter as hot air to the dehumidifier. So the highest temperature is here. T maximum is at this point in this cycle. And it is going to effectively heat the water, and the hot water is going to enter here. This hot water is going to be sprayed, and it will heat the air which is coming in. So we're talking about air is going to be heated to about 80 to 90 degrees centigrade. It might heat the water to about 60 degrees centigrade or so. So water at 60 is going to be sprayed, and air at a temperature of about 30 will be entering in here. So what will happen? Air will be heated and humidified in the humidifier. Are we going to use the same figures? No, but we are going to use similar figures. So for air heated cycle, we have figures that are similar. They are not exactly the same because definitely the nature of the cycle is the same. But for you, the procedure is going to be the same. What you need is the effectiveness of the dehumidifier, the effectiveness of the humidifier, so that you can get the value of the GOR, the effectiveness of the dehumidifier and the humidifier, so you can get the you can get the optimum mass flow rate ratio, effectiveness of the dehumidifier, and then you can get the recovery ratio. So exactly the same steps that we did earlier, but the difference here is that these are made for an air heated cycle.
Doctor, sorry, is it efficient to use a cooling system instead of heating system? I mean, for the air.
Where?
In the air side between the humidifier and dehumidifier. You're next to the fan.
Air is able to take moisture as long as it's hot. When it is cold, it does not. For example, and this is why, if you remember, we talked about that earlier, when you are going out in a humid day with relatively low temperature, you'll find that there is surfaces are wet, which means that we have reached that dew point and water vapor in the air has condensed. So air cannot carry much water when it is cold. In order to enable the air to carry more water vapor, you have to heat it up. And that's why we need to heat the heat in this system. So cooling down is going to be good for the water that comes in here. Because if you guarantee colder water running inside the pipes, then the condensation is going to be effective. But you cannot cool the air here. Did I answer your question?
Yes, thank you, Doctor. I'm talking about by the way, the one in between the humidifier and the humidifier. It's not the heat.
You mean
Yeah,
here?
this one. Yeah, here.
You are not going to get much benefit, because if you cool the air, it means that you're going to need more heat here to heat the air. So we're talking about excessive energy that will be needed for cooling and then for heating, because when air enters here at a temperature 30 and water is sprayed at temperature 60, maybe the air will go out at a temperature of 50. But if you cool the air to a temperature of 15, then in order to bring it to 50, you need much higher rating for the heater. So this is going to be much higher energy spent to the system.
I see. Thank you, Doctor.
You're welcome. Now, we have done these calculations, and based on that, we obtained the water flow rate and air flow rate. We sized the system again. Look at the height in the humidifier here. For the water heated cycle, we needed a packing height of 1 meter. Here, only you need 15 centimeters. This is one major difference between them. On the other hand, for the water heated cycle, we needed an area of about 11.7 or so meters square in the dehumidifier, but here we are needing 46 meters square. So in terms of capital cost, in the water heated cycle, you need a big humidifier, small dehumidifier. For the air heated cycle, it's the opposite. But anyway, the prices are basically not going to be much different. On the papers, air heated cycle can give you a little bit of higher gore, but in reality, air has a problem of being related to leakage to the surroundings and related to being having a small heat capacity ratio. The specific heat of the heat is small. Cp is equal to about 1 kilojoule per kilogram Kelvin. For water is 4.2. So water is better in carrying the energy than the air. And that's another issue. One more thing for the air, blowers are huge and they consume lots of energy compared to pumps. So it's better for us to pump water which is hot than blow an air which is hot as well. Then this is going to consume much more power. That's a comparison between the performance of both of these, the water heated and the air heated cycles. We're talking about fresh water production of 10 liters per hour or kilograms per hour. On the papers, it shows that the air heated cycle is slightly better in terms of gore, but this, I assure this is only on the paper, because having to build that in a real system, then sizing of the blower is going to be a little bit different, and then the kind of energy input that we are not considering in the gore. In the gore, we are only looking at the QN, but we are not adding power of the pump and the power of the blower, which might change the picture from this. And then the optimum mass flow rate ratio for the case of water heated cycle, it's 2. For the air cycle, it is 0.66, which means that for the air heated cycle, we are using more air than the water. And that's why the size of the blower has to be higher, which is not accounted in the gore. But if we do that, then the Gore values are going to change. The heat input is not really much different. It's about 3 kilowatts for both of them. The feed water supply is not much different. Circulated flow rate of the air is different. Here in the water heated cycle, we needed only 0.04 kilogram per second of air. But for the air heated cycle, we needed 0.1. So we're talking about something like, is it almost 3 times the flow rate of the air needed? And this is a substantial energy addition in the air heated cycle. I would have I can now think that we seriously have to recalculate the Gore by considering as the Gore definition to be written as m dot fresh water into HFG divided by the energy N rather than the Qn. The energy N here should be the Qn by the heater plus power of the pump plus power of the blower. If we do that, then the Gore for the water heated cycle, it will be a little less than that, definitely, but it will be definitely higher than the one for the air. Then we are talking about the dimensions of the unit, which are basically same width, but the height is different. It's about 1 meter for the water heated cycle. I'm talking about the humidifier, only 15 or 16 centimeters for the air heated cycle, but the heat exchanger is much bigger in the air heated cycle than the water heated cycle, and this is actually going to add to the cost of this air heated cycle much higher than the water heated cycle, because this is an expensive component. So the tables is showing that both of them are having close values of the Gore and the energy input. Optimum mass flow rate ratios are different. Considerable larger volume of the air is needed in the air heated cycle. Pumping power is going to increase drastically in the air heated cycle. The water heated cycle is going to have slightly bigger humidifier. I talk about 1 meter height of the humidifier. And the air heated cycle needs a smaller humidifier basically. So that was some sort of a typical design condition. You might have a case like this given to you, for example, in a homework or a quiz or exams, where I provide you with these figures and I ask you to go through the calculations that we have done here step by step. This is one way of the analysis of the HDH cycles, in which what we are looking for is how to design a cycle, how to come up with the size of a cycle. There is another class of problems that we might be starting with on Wednesday, and this class of problems is basically considering what if you have an operating HDH system which is running, how you can analyze it, how you can come up with the Gore and the flow rate, the flow rates would be given, how you can come up with a Gore and the effectiveness, for example, of different units within the system. I put that example on the blackboard, and what I'm going to do is we're going to start with that example next time. I would hope that next time you have like a pen or a pencil and a blank sheet of paper, so that you can go through the example solution step by step with me. That's going to make it easy for you to analyze problems related to the HDH. So for the HDH, or the humidification, dehumidification, desalination system, we are basically exposed to, number one, looking at different layouts of the cycles, having an idea about the analysis of the cycles. Number two, we are looking at design component of a cycle, which is what we have covered today. If I need to design a system to provide me with a certain flow rate, then how to proceed using this graphs as aids to enable me to analyze the problem easily. And the third thing is whatever we are going to do next time, inshallah, in which we are going to look at a numerical example. We are going to solve the example together by numbers, and then we are going to analyze the performance of existing unit. In heat transfer course, you have taken, when you studied heat exchangers, you have studied basically rating versus design of heat exchangers. This is basically what we are doing here. A humidifier and a dehumidifier are both heat and mass exchangers. Today you have gone through the process of design. Next time we are going to do the rating, inshallah, so that you can see how the evaluation performance can be done for these units. Any questions?
Doctor,
Fadal.
regarding the example that will be solved next class, it's the one in called example on HDH systems.
Yes, exactly. It's in the blackboard.
So we will be working together to find everything that we studied today, for example, using the graphs, and we will apply it on that example.
No. What we studied today is a design case.
Exactly.
And the numbers for the design case are given to you here. So the example that we have gone through today is an example of a design case.
Yes.
What we are going to be doing next time is a different example. It's a rating example. Here we started from nothing and we need to come up with a unit. So what is the dimensions of the units and what are the physical flow rates? Next time, the units working, the units are there. Flow rate
will be running.
But they are running already, and we need to see how good is that running.
Okay, understood.
As if you are going to the lab and you are running a heat exchanger, for example. Now we are running the unit with a mass flow rate ratio, which is the optimum. What if the unit is not operating at optimum mass flow rate ratio? Sometimes, due to whatever reason, you have changed the flow rate of the water or the air. The unit is going to work. It will not stop working, but the performance parameters are going to change. For a case like this, how can you evaluate the performance of the unit? This is rating, performance rating is, and this is what we need to do next time, inshallah.
Okay, understood. Thank you.
You're welcome, sir. Any other questions? Shabab? If not, then that would be it for our class today. As usual, I'll be hanging out for about 5 minutes or so if you have questions. And we'll see you on Wednesday, inshallah.
One more question, Doctor. If you
تفضل يا خالد.
زاد فضلك. You mentioned earlier today class that you can simplify if you don't have the, let's say, the what we call the heat transfer coefficient, then you can simplify that by adding by replacing it with CP times the difference in temperature, right? This is applied.
It's not the heat transfer coefficient, it's the enthalpy.
Sorry, the enthalpy, yes.
For example, the delta H, the expression of delta H is basically can be given as CP delta T. As you have taken in thermodynamics, if you remember that.
Yeah.
Yes. Something like that, H2 minus H1 is equal to MCP T2 minus T1. And this is fine as long as you are talking about water. But we cannot do it for the air. Because for the air, it can be done only for dry air. We are not dealing with dry air in our analysis. Our analysis basically is both heat and mass transfer. So the equation that I'm writing here, this can be used for water only. Not for the air. And for the air, the enthalpy becomes a function of not only temperature, but temperature and humidity.
All right, I see, Doctor. Because I thought we could use it also for the air, but
no, we cannot, because you can use it if you are talking about a problem in thermodynamic course where we are only considering dry air.
So only it's a function of one parameter, which is temperature in this case.
Yes, exactly. It becomes a function of temperature. But for air, no, you cannot. Because the enthalpy of the air is going to change if you change temperature, or if you change humidity, or if you change both. You can have a look at the psychometric chart, for example, that will give you an idea here. Because on the x-axis, you have temperature. On the y-axis, you have absolute humidity. And the enthalpy is going to change when you are changing any one of them.
Cool. Thank you, Doctor.
Did I answer your question? Is it clear now?
Yes. Thank you so much.
For
It is
example,
really.
this is what I was going to put actually, is that the psychometric chart looks like this, and this is omega and this is T. If you move here, you are changing temperature at constant omega, and the value of H will change. If you are moving in this direction, temperature is constant, omega is changing, but H is also changing. So H here, or the enthalpy, has to be a function of both parameters. تمام؟
Yes. Thank you, Doctor.
You're welcome.
Doctor,
اتفضل.
but didn't we consider the dry mass flow rate of dry air?
Yes, I mean, this is, for the analysis, you have one of two things to do, Ya Saleh. Either to do the analysis and write, for example, that the enthalpy of the air is enthalpy of dry air plus enthalpy of the water vapor. And you keep on doing that. For this, the enthalpy of dry air can be written as Cp delta T, if you wish. But H here, you have to add two components together. You have always to look at this or that. Or alternatively, you can get the total enthalpy, which is based on humidity and temperature, which is what we are doing.
Okay.
And we keep on the circulation of the unit is basically dry air. This dry air is going to carry some water vapor in the humidifier, and it will leave this water vapor in the dehumidifier. Area of the dry air is always the same. The mass of the dry air, mass flow rate is always the same. But here it is loaded with water vapor, and here it leaves the water vapor. So properties of the dry air are going to change. I'm talking about thermodynamic properties, are going to change based on its temperature and how much humidity does it have. But the mass flow rate will be always mass flow rate of the dry air. If you wish, you can get back to the Thermo 2 psychometric chapter and just revise it quickly. Then you can see that. You have even processes there of a process where you have like a channel here. This channel has a heater and it has a humidifier, and then air is passing, and then you are looking at the psychometric changes here. And the same thing, you can have a channel with a cooler, a cooling coil, and then a dehumidifier. And then you are considering the inlet versus the exit. So these things you have covered already, and you have two ways to do it. Either to consider or to divide the unit into, to divide the process into heating and then humidification, or cooling and dehumidification, or take it as one unit in which you are looking for how the enthalpy is going to change. But the mass, which is going here and here, we are relying on it as the mass of dry air. Did I answer a question, Saleh?
I remember that question. Could I ask another question?
Yes, go ahead, please.
Could you explain more the note, the fifth note and sixth note?
What is it?
The fifth note and the sixth note. From notes, we take it. The last notes about the design example.
What do you mean by 5 and 6? وضح لي شوية يا صالح. خليني
اللي هو الملاحظة الخامسة والسادسة اللي ذكرناه في الديزاين اكزامبل.
طب خليني افتح الديزاين اكزامبل وقول لي عليها اي واحدة اللي تقصدها. ده الديزاين اكزامبل اللي احنا مرينا عليه.
السلايد الأخير.
السلايد الأخير هنا.
أيوة الملاحظة الخامسة والسادسة لا تبدأ.
Basically what we are doing here يا صالح is that we are doing a comparison between the water heated cycle and the air heated cycle, and this comparison is based on the values that we have seen in this table. So we obtain that table, and looking at it, we're trying to identify, based on a comparison, what are our observations here. And through the observations, we have seen that for the water heated cycle, the humidifier size is big. We agreed that in the humidifier, basically, we have dimensions for both water heated cycle and air heated cycle, such a way that it is 25 by 25. So the cross-sectional area is the same for both units, but the height is different. For the water heated cycle, we needed a height of about 1 meter. For the air heated cycle, we needed a height of 0.16 at all. Why is that? This actually is related to the flow rates which are there. Remember, in the water heated cycle versus the air heated cycle, for the water heated cycle, the mass flow rate ratio was about 2. For the air heated cycle, the mass flow rate ratio is about 0.6, which means what? It means that we have here more water is passing, and here we have less water and more air is passing. And this is related to this. If you have less water, then you don't need very high packing material for the transfer of the mass for the evaporation to occur. Here we have more water, and for the more water, you had the water to be sprayed or spreaded on a larger surface area for effective evaporation to occur. And that's why when you are looking at the water heated cycle, the humidifier volume needs to be bigger. You have more water there. And more water, it is creating higher pressure drop of the air, which is fine. We are not looking at the pressure drop at the moment, but we are looking for a flow rate ratio of about 2. So the flow rate of the water is twice the flow rate of the air. We have more water. You need to provide more opportunity for the transfer, for the evaporation to occur. What does the packing material do? It is just a surface area for the water to stay on. So you needed larger surface area because you have higher flow rate of the water, so that you have a film of water on these surfaces that transfers heat and mass to the air. For the air heated cycle, it's the opposite. The flow rate of water is less. It's about half or more than a little bit of half of the flow rate of the air. So you don't need all of that height.
I see.
Is this point clear, Saleh?
Yes.
Okay.
Thank you.
When we are talking about the air heated, yes, that's basically that takes care of the 2 points, 5 and 6. You have further question?
Thanks, Doctor.
You're welcome. ما سألتش النهارده عبد الكريم. Anything not clear?
Yes, indeed, I have about the effectiveness.
Yes.
Imagine we have a heat exchanger of cross flow.
Yes, but before we continue with imagination, I have to tell you something. What we are dealing with as humidifier and dehumidifiers are not heat exchangers. They are heat and mass exchangers. So we are talking about heating and evaporation, and we are also talking about cooling and condensation. That's why it's a little bit different. But the definition generally is that effectiveness is delta H actual over delta H maximum. And the delta H maximum is an imaginary sort of higher limits, something like the Carnot cycle. You can never have a cycle running at Carnot cycle efficiency, but we use it just for the sake of comparison.
So when we say the effectiveness is 1, it is as if the hot inlet temperature is equal to the cold inlet one.
Inlet air temperature, for example, if you are talking about a humidifier. يعني الهيوميديفاير بقى الأداء بتاعه سوبر لدرجة إنك بردت المية إلى أقل درجة ممكن توصل لها. Actually that will never happen إلا لو عندك humidifier السايز بتاعه
infinite long.
بالظبط infinitely long.
اه
وانفينيتي لونج دي كويسه قوي على الورق وكويسه قوي في الفيزيكس، بس فور انجينيرنج مفيش حاجه اسمها انفينيتي لونج. انت خدت في الهيت ترانسفير اناليسيس بتاع الفنز الاكستندد سيرفيسز،
ايوه
وقلت والله الافكتفنس بتاعت الفن او الاناليسيس بتاع الفن بيقول ان درجه حراره التيب بتاعت الفن is going to be reached when we are talking about infinitely long fin. هو في حاجه اسمها infinitely long fin؟ fins are normally short. بص على الموتور بتاع الدباب اللي هو الموتوسيكل. الموتور ده كفرد بفينز، طول الفين قد ايه؟ ما يزيدش عن 10 سم.
صحيح.
cannot talk about infinitely long fin. كلمة infinite هنا ملهاش معنى.
يعني مش 5 متر او 10 متر، هذه يعني انفينيت رقم كبير.
بالظبط. الانفينيت بالنسبة لنا كانجينيرنج بقول والله انا لو خليت الفين دي طولها 10 سم، انا بدل ما اوصل لدلتا تي سي مثلا درجه السيرفس درجه حرارته مثلا 70 والهواء درجه حرارته 20، يبقى الفرق بينهم كام؟ 50. انا هقول بدل ما الفرق بتاع 50 لا انا هضرب فرق 45. الفرق اللي هو 45 ده هيديني فين طولها 10 15 سم. That's good enough. يبقى دي الانفينيتي بتاعتي. ف I need to come up with something sensible. لما اتكلم هنا على الهيموديفاير واقول عندي infinitely long ولا infinitely high heat exchanger، انا هدفع فيه كام؟ ثمنه هيبقى كام؟ وبالتالي ثمن الكيوبيك متر اوف ووتر هيكون كام؟
فاهم.
وبالتالي I have to come up with something that would make sense from the engineering point of view.
I can see now. Okay. Another one is that if we minimize the S generation or the exergy
نعم.
destruction.
قلنا الاكزيرجي ديستراكشن كويس.
يعني how will this affect the heat transfer?
Actually the point هنا يا عبد الكريم كنت تبص لها من ناحيه how you are going to better design a unit. انت ممكن تعمل ديزاين فور هيت اكسشينجر، تعوز الهيت اكسشينجر ده يكون ضخم جدا، او ممكن نفس الافكتفنس if you have a better design of a smaller heat exchanger in a way that you are minimizing الاسباب اللي بتسبب الانتروبي جنريشن. الانتروبي جنريشن بتيجي نتيجه ايه؟ نتيجه الهيت ترانسفير، نتيجه الاكسبانشن. اكسبانشن يعني ايه؟ يعني لو هستخدم هواء يبقى الهواء ده ما اعديهوش من ماسوره مثلا الدايمتر بتاعها 4 انش وادخله في تانك ضخم بحيث ان هو يحصل له اكسبانشن. لا انا اخليها جراديوال، وبالتالي انا بقلل الجنريشن اوف انتروبي اسوسييتد وذ اكسبانشن. نفس الوقت I try to keep on السايز بتاع الميكسنج بتاع اليونتس is done in a way that does not generate much entropy. وبالتالي you keep on the quality of energy in mind. واحدة من الأفكار اللي هي بتساعد في إن إحنا نقلل الانتروبي جنريشن في ال HDH unit إن إحنا بصينا لقينا إن الانتروبي جنريشن is minimized لما تكون الهيت كاباسيتي ريشيو is close to 1. هيت كاباسيتي ريشيو اللي هي ايه؟ اللي هي الريشيو الام دوت سي بي بتاعت الهواء مثلا على الام دوت سي بي بتاعت الميه. لو الفاليو دي قريبه من 1 يبقى انا عندي الانتروبي جنريشن is minimum. طيب الفاليو هتكون قريبه من واحد ازاي؟ اذا كانت الميه عماله تتبخر باستمرار جوه الهيوميديفاير وعماله بتتكثف باستمرار جوه الديهيوميديفاير، يعني الماس فلو ريت ريشيو بتتغير. اذا جت الفكره بتاعت اللي احنا بنسميها ثيرمودايناميك بالانسنج، والفكره دي حتى احنا عملنا لها يعني اتس باتنتد في اكتر، حتى الباتنتنج اتعمل في اكتر من دوله، ان هو انا بعمل كونكشنز ما بين الهيوميديفاير والديهيوميديفاير وبقول ده انجكشن اند اكستراكشن او ثيرمودايناميك بالانسنج، ان انا بسمح للفلو ان يسيب واحده من اليونتس يروح لليونت الثانيه in the middle of the process، بحيث ان انا I try to maintain ال heat capacity ratio is as close to 1 as possible. And this should to be an effective way of improving the performance. احنا حتى جربناها experimentally. We did some experiments that shows that yes, through this balancing you can improve the gore by something like 20 to 25%.
So يعني at the end if we minimize the entropy generation it will يعني highly
The performance, the unit is going to perform better. Yes.
the unit is going to perform better in terms of GOR.
In terms of GOR نعم. انت ممكن ما تكونش بتغير السايز بتاع اليونتس، بس you are designing اليونتس بحيث ان انت you are allowing that flow of the vapor from one component to the other في نص البروسيس، يعني اعمل في نص الهيوميديفاير والديهيوميديفاير اعمل كونكشن بينهم او connections in different places. ومساله البليسز دي حتى فيها study، طب انا افضل مكان اعمل فيه الكلام ده قد ايه؟ it depends on the size of the unit، وهل انا محتاج connection واحده ولا اكتر وهكذا.
فهمت. I see. Just a final one. Why we take m.air as reference?
We don't take it as a reference. احنا في العاده بنستخدم m dot او mr mass flow rate ratio، اللي هي مثلا بنقول mass flow rate ratio بتساوي 2 او 3 او 4 او 0.6 زي ما شفنا في الاير هيتد سايكل. بس practically speaking عشان الماس فلو ريت ريشيو احكمها قدامي حاجه من اتنين، يا اما اثبت الماس فلو ريت بتاعت الهواء واغير بتاعت الميه، او اعمل العكس. practically speaking على الارض في المعمل اسهل لي ان انا اغير الماس فلو ريت بتاع الميه عن اني اغيرها بتاعت الهواء. انا افضل لي ان اخلي الهواء بالذات في الاير هيتد سايكل لو عندي الكتريكال هيتر، لان انا لو قللت الفلو ريت بتاع الهواء ممكن الالكتريكال هيتر يتحرق، بيحصل له اوفر هيتنج ويتحرق. اذا افضل لي ان انا اخلي الماس فلو ريت بتاع الهواء ثابت وعند درجه حراره كافيه تمتص الحراره اللي بتطلع من الهيترز، واغير الووتر فلو ريت بسهوله بان انا اعمل باي باس للووتر. So practically speaking it's easier to control الفلو ريت بتاع الميه عن controlling الفلو ريت بتاع الهواء.
يعني if I have an air that's not dry and for example I have the enthalpy 1 and enthalpy 2, I have to multiply by m dot air.
Yes.
Not
m dot air into the enthalpy. نعم، عشان تجيب التوتال heat transfer او التوتال enthalpy change as you one state to the other. مفيش حاجه اسمها dry air يا عبد الكريم. مفيش dry.
I see it.
You have either low humidity او high humidity، بس مفيش dry air.
مفيش dry. طيب والام اير يعني هي داخلها ووتر وايضا اير.
ما هو الاير ماشي وشايل معاه شويه ووتر فيبر.
ايوه.
humidity. انا بزود الهيوميديتي في الهيوميديفاير وبرجع اكثفها تاني في الديهيوميديفاير. تمام.
ايوه هذه اللي انا متخيلها. بس يعني اذا كان انا عندي الانثالبي 1 والانثالبي 2 both يعني point have air also vapor water. If I want to find يعني the number in terms of joule I have to multiply by m dot mass. But why this m dot mass only dry air, not
انت
air plus
انت قدامك
vapor؟
تعمل حاجه من اتنين، يا اما تقسم الهواء لتو بارتس وانت بتحسب الانثالبي، تقول انا هحسب الانثالبي تشينج بتاعت الدراي اير اللي هي سي بي دلتا تي، وهحسب الانثالبي تشينج بتاع الووتر فيبر لوحده، واجمع الاثنين على بعض عشان اشوف التوتال انثالبي بتاع الاير. يبقى انت عملت ايه؟ ازف ان انت قسمت الاير ستريم لجزئين. الكلام ده مش براكتيكال، الكلام ده على الورق بس. كويس؟ فانت قلت الاير بتاعي عباره عن دراي اير زائد ووتر فيبر. الانثالبي تشينج اوف ذا دراي اير از ام دوت اير سي بي دلتا تي، والانثالبي اير بتاع الووتر فيبر هيبقى عباره عن، هتشوف كام الانثالبي تشينج بتاع الميه، كانت درجه حرارتها كام ووصلت لكام، وتجمع الاثنين على بعض. او ان انت الاسهل ان انا، عشان كده اتعملت سايكومتريك تشارت، ان انا يكفيني ان انا يكون عندي جهاز يقيس لي قد ايه درجه حراره والرطوبه بتاعه الهواء، واخد درجه حراره والرطوبه النسبيه دول وادخل جوه السايكومتريك تشارت احدد الانثالبي على طول. الانثالبي هتبقى توتال انثالبي اوف دراي اير اند ذا مويستشر ان ذا اير. عشان كده قلت لزميلك ان ارجع بص تاني على الكتاب، على كتاب الثيرموداينامكس، على الشابتر بتاع السايكومتريكس، هتلاقي الجزء ده يمكن مشروح هناك بشكل موسع شويه.
صحيح صحيح صحيح. شكرا لك، الله
عفوا.
يعطيك الف الف عافيه.
الله يعافيك. محمد معانا ولا بس الاسم ظاهر؟ محمد الغامدي.